Welcome to the design and control of concrete mixtures. This presentation will cover Chapter 2 on sustainability. This chapter will provide an introduction to sustainable development and concrete's role in sustainability. In the pioneering report of the World Commission on Environment and Development, Our Common Future, sustainable development is defined as meeting the needs of the present generation without compromising the ability of future generations to meet their needs. Embedded in the concept of sustainability is a balance of social, economic, and environmental principles. The leading nationally recognized sustainability programs focus primarily on energy conservation and atmosphere, water management and resources, site selection and development, indoor environmental quality, and material quality and resources. Another factor that is increasingly coming into play is functional resilience, or the ability of a structure to serve the original purpose and be adapted for future use. Several organizations have developed rating systems that attempt to quantify improvements in green performance. For example, concrete use can contribute to credit in 15 categories in the United States Green Building Council's leadership in energy and environmental design for new construction and major renovations. The principle of sustainable development. The principles of sustainable development are easily incorporated in the design and proportioning of concrete mixtures and exhibited readily through applications and service. Durability is one of the most important contributions to sustainable development. This translates directly to longevity of the structure. A structure that satisfies the needs of several generations is considered a sustainable development. Properly designed reinforced concrete is resistant to storms, floods, fire, and earthquakes. These structures can also provide blast protection for occupants. The concrete home shown here, still standing, survived a tornado in Wisconsin. Concrete can enhance overall energy performance in several applications, including thermal mass, fuel consumption, heat island reduction, and lighting efficiency. Insulating concrete forms, shown here, provide thermal mass and high levels of insulation, key components for net zero energy buildings. One of the key aspects of thermal mass is it can shift energy demand to off-peak time periods as shown in this plot. Studies demonstrate the lower fuel consumption for vehicles traveling on concrete pavements. Current research shows an increase between 1 and 11% for heavy trucks and 3 to 17% for smaller vehicles. Light-colored concrete materials have higher solar reflectance, also called albedo, which reduces the heat island effect. The picture here shows a thermal image of a pavement transition in Mesa, Arizona. Note the temperature difference between the concrete pavement and the asphalt pavement. The SRI of new concrete greatly exceeds the threshold value of 29 for most green building standards and rating systems. Concrete contains low to negligible amounts of volatile organic compounds. Decorative concrete flooring, created using a sandblast stencil technique, eliminates the need for carpeting or other flooring materials that can impair indoor air quality. Concrete can provide excellent acoustical control. The STC value is roughly the number of decibels that sound is reduced going through the wall. Cast unfinished concrete has an STC ranging from 44 to 58. If the wall is then dressed with furring, insulation, and wallboard, the value jumps to as high as 63. In addition to building acoustics, concrete is used as highway sound barriers, and many methods have been developed to produce quiet concrete pavements. Pervious concrete allows for infiltration of water, reducing runoff from the site. The image on the right shows a side view of water percolating through pervious concrete. An alternative to pervious concrete is a permeable grid paver system. Interlocking concrete pavers allow water to infiltrate between the units. Green roofs can be made to support small plants and shrubs, or built to support much larger vegetation. The image shows Chicago's Millennium Park, which is an extensive green roof covering a commuter rail station and 2 parking garages. Concrete cisterns collect rainfall and store it for later use in non-potable applications, such as toilet flushing and irrigation. Treatment systems can purify the rainwater suitable for drinking, bathing, and other potable uses. Cement-based solidification stabilization treatment is well suited for remediation of brownfields and has been successfully implemented in a number of brownfield sites. Many concrete materials can be recycled after initial use. Concrete from demolished structures can be recycled and is commonly reused as fill or road base. Paving trains can recycle existing concrete pavement. The crushed concrete can be used as aggregate in new concrete or as base material. Many concrete structures already incorporate one or more forms of pre-consumer recycled materials in the form of industrial byproducts. Also, many cement plants utilize industrial waste and discarded tires as alternative fuels for the kiln. Most of the components of concrete are manufactured within 500 kilometers or 300 miles of a concrete plant. Most ready-mix concrete plants will be within 150 kilometers or 100 miles of the project site. These short distances minimize fuel requirements and associated energy and emissions from transporting and handling. During the life of a concrete structure, the concrete absorbs carbon dioxide in a process called carbonation. This may be viewed as a loop in the carbon life cycle, as it reabsorbs much of the carbon dioxide that was released during the calcination of limestone in the cement manufacturing process. A key benefit of concrete is the ability to modify the concrete constituents and proportions to best meet the sustainability goals of a particular application. 2 examples are cement and aggregate. Both of these ingredients can utilize recycled materials. Life cycle analysis is a tool used to select building materials and influence design choices. A life cycle cost analysis is the practice of accounting for all expenditures incurred over the service life of a particular structure. A life cycle assessment, or LCA, is an environmental assessment of the life cycle of a product or process. A life cycle inventory, or LCI, is the first portion of an LCA. It includes all of the materials and energy inputs as well as any emissions to air, water, and land from the various stages shown in this graphic. An LCA provides a consistent methodology applied across all products and at all stages of their production, transport, use, and recycling at end of life or disposal. This table demonstrates the life cycle phases and components for concrete pavements. This table demonstrates the life cycle phases and components for concrete buildings. At the Massachusetts Institute of Technology Concrete Sustainability Hub, a team of professors, researchers, and students are using LCA to evaluate and improve the environmental performance of buildings and pavements. Preliminary analysis from MIT indicate that the operation components of the infrastructure, primarily heating and cooling systems for buildings and rolling resistance for pavements, hold the most potential for large-scale improvement. In summary, this chapter provided a brief introduction to the principles of sustainability and sustainable development, and briefly touched upon the sustainable development rating systems that are used today. It covered in brief detail a variety of ways in which concrete passively and actively is involved in sustainable development, and then closed out with a discussion of life cycle analysis. If you have any questions, please write them in your journal so that we can discuss them in our next class.